So let's continue our discussion of conic sections. So last time we arrived at this equation, x squared plus 1 minus lambda squared y squared minus 2y plus 1 equals 0 for this conic section. And it turns out that any sort of parabola or ellipse or hyperbola can be written in anything you can get of this locus form can be written. Anything in this form that is one of these and not something boring like 2 lines or a point will have this locus form. But this doesn't really tell us when we get what. So so the hyperbola will be something like this, and it'll have points on the other side too. So to have this, if we take a point P on here, we need PA. That's necessarily going to be greater than this distance if it's on the opposite side of L from A. This is clear from the diagram that PA will be greater than delta PL. And what this implies is that lambda, which is PA over delta PL, will be greater than 1. So we're going to have the hyperbola in the lambda greater than 1 case. Now, what if lambda is less than 1? Then what happens is you can't go off to infinity, because if you take a point P that's too far away, you're going to need PA. PA is going to be at least the distance here minus the distance from A to L. Assume on this side, in the case where lambda is less than 1. So to have this, in the case where lambda is less than 1, rearranging terms, we get this. I suppose I should erase this. Rearranging terms, we get this. And since this is positive, we can now divide both sides by it without changing the direction of the inequality sign to get this. So this is a finite number. So we have this upper bound on how far away P can get. So it's not going to go off to infinity in the vertical direction. So it turns out that this will correspond to the ellipse case. And so actually, I wasn't quite accurate when I said before that anything you can get by this curve or any of these conic sections subscribe to the locus definition. Because there's one special type of conic section, the circle. And this locus definition doesn't really work well with it. What you end up wanting to write, I believe you turn out writing some nonsense like the distance from P to A is equal to 0 times the distance from P to infinity. Something nonsensical that makes no sense. But it turns out that that's a valid conic section. So pretty much almost all conic sections have this locus definition. So anyway, in this lambda less than 1 case, we get the ellipse. And this isn't a formal proof, but it just shows you what's going on. And so we've got one case left and one curve left, the parabola. So by the process of elimination, or perhaps you'd want to do more rigorous reasoning, you should, the curve corresponding to the lambda equals 1 case is the parabola, which is, so we see this quite simple definition of a parabola as the curve that is of all points that are the same distance from a given point and a given line not passing through that point. This is called the focus of the parabola, and this is called the directrix. These may apply to all conics, but I'm not really sure. You'll want to check Wikipedia or something for that. But anyway, this shows you what more of the correspondence between the locus and the algebra. But we still haven't talked about the actual cones. And we'll get to that in our next video. So stick around for Conic Sections Part 3. Thank you for watching, and I hope you follow me on Twitter at Luke Robitaille. That's not Luke_Robitaille. Thank you.